Number 85 is a really hard question because it, first of all, has all this language in here about how AIDS testing works and antibodies, which honestly is related to how antibodies for the coronavirus seems to work. But either way, it's talking about false negatives and false positives. So when you get this result, how trustworthy it is, how frequently it is actually not giving the truth value to it. So what is confusing to me is if you look at this table, it's so tempting to want to consider this as a two-way table. But two-way tables we use for frequencies, for counts, and if you count these up, if you call these percentages, which you can read these as percentages, then you end up having a total of 200%, which doesn't make sense. So we need to think of this more as like a conditional probability table, which we haven't used it like that, so I'm just not going to. I'm going to use our tree diagram for that. It is much more, I wouldn't say easier, but it's less misleading than if you try and use it with this table. So it's possible to do with the table, but like I told you in class, I used to try and do these exclusively with tables, and it's confusing and hard to do, so let's just not do it. I'm going to use it instead to find this probability. I'm going to use the tree diagram, that is, to find this probability. And it says, we're finding the probability that they have the antibody, but this is if the person is already positive. So this is a conditional probability. We talked about the formula for that is to find first the probability that both events are true, the probability that somebody has the antibody and they're HIV positive. And then you divide by the probability of the conditional event being true. Divide by the probability that they are positive in the first place. So I need to look at this tree diagram to figure it out because 1% of the population carries antibodies. So that's part of one thing that's not in this chart. It says antibodies present. 100% of those people are either going to be positive or negative, but it's not including this 1%. So I'm going to just put it on my table. So 1% of the population will have the antibody in their blood, so 99% don't. But now that I know that there are antibodies, the table is telling me that the test will read positive results, 0.9985 for those antibody-full people. It'll tell them they're negative, which is not the result that is accurate, less than 1% of the time, but it does happen. Similarly, if you do not have the antibodies in your blood, this is saying that the test will tell you you do 0.006 is your probability, so 0.6% of the time. It'll be accurate and tell you it's negative for antibodies, the remaining 0.9940. So these conditional probabilities were all found in this chart. So now I'm going to find the probability first, again, of antibody and positive. So I'm just going to go down that row of first somebody having the antibody and also testing positive. When you go down these rows, we multiply those probabilities. So this is going to be 0.01 times 0.9985. That's just one way to end up with a positive test reading. So I also could end up positive with this path. So if it's one or the other, that's the ways that this could be positive. So you could be positive with antibodies or you could be positive with no antibodies. I'm going to put those two different options being added together down here. So either I have antibodies and I test positive, or plus I don't have antibodies and I test positive. So you're just going to have this quotient. Be careful putting that in your calculator, but it should give you 0.627. So this is saying that given this test gives a positive readout, there is a 0.6275 probability that the person has the antibody.